Okay, we will do this question. This is, I hope, assignment 3, question 2. This question is related with frequency modulation. So this is our message signal. This is our message signal, and this is the amplitude of the message signal. And this is 25 FMT form. Okay, so this is our message signal frequency. Okay, and this is our carrier signal. So the amplitude of the carrier signal is this 40, and this is the frequency of the carrier signal, FC. Okay. So we will try to do this. Okay. So we know that the general form of FM modulated signal, it is like this. X FM T or something. So this is frequency modulated signal is equal to AC cos omega CT plus 25 F delta integration within T. This is the time of the message signal, and it is X, let's say tau, T tau, D tau. This is the general form of the modulated signal, frequency modulated signal. Okay. We know that this is frequency deviation, F delta is frequency deviation. And if frequency deviation is divided by the message signal frequency, we will get modulation index. So this is the modulation index. And we also know that if we consider this frequency deviation, F delta, it is equal to Kf of AM. No, so this Kf is phase sensitivity. Sorry, frequency sensitivity. Frequency sensitivity. This is message signal amplitude. Message signal amplitude. So if we have F delta, that is frequency deviation, the modulating signal amplitude is there. Okay, so this should be the nominalized signal. No, this should be the nominalized signal, message signal. Okay, so that's idea we need. Okay, so we know that the frequency deviation should be less than carrier frequency. Actually, this is the frequency deviation should be very less than the carrier frequency. Okay, so anyway, this is the maximum. This is the upper bound. This is upper bound of the frequency deviation. Upper bound of F delta. So upper bound of F delta is nothing but the carrier signal frequency. Okay, and also we know the relationship between the modulation index and frequency deviation. So we have F delta less than FC. Okay, if we divided this by FM and if we divided by this FM, what is this? This is frequency, sorry, modulation index. So this is the upper bound for frequency modulation index. No, so upper bound for frequency modulation is frequency modulation index is upper bound for frequency modulation index. Okay, so this is modulation index MF. The upper bound is FC by FM. Okay, so here we have FC 1000, now 10,000, that means 10 kilohertz, and we have 100 hertz FM. That means 0.1 kilohertz. So this is the frequency index. No? Upper bound for frequency index is, this is upper bound. So frequency modulation index is 10 by 0.1, that is 100. So this is the upper bound. Okay. And so we can write the modulation waveform also. Okay. So we have our so we have our message signal xt, that is like this, AM cos 25 FMT type. Okay. So this is only one sinusoidal signal. So this is called one tone. No? This is one tone. So this is one tone modulation. Okay. So you can see that to write the waveform, we need to get the integration of this message signal. Okay. So if I get the integration of this message signal, I will have, so I will get the integration. Okay. So I will write down here d tau x tau 0 to t maybe. Okay. So here we have AM sine 25 FMT FM tau. Okay. Because I have just changed the independent variable to tau, because it is mesh with this t. Okay, that is why I change this t into tau. Okay, some in your lecture note, I think it is in lambda form. No? Instead of this tau, the lecture note use lambda. Okay, don't confuse with that letter. Okay, it is just to represent the independent variable. Okay, AM sine 25 FM tau divided by 25 FM. No, correct. So this is from 0 to t. So that means we have AM 25 FM sine 25 FM t. No, so here t, and if we substitute the 0, sine 0 is 0, so we have only this term. Okay, so this is the integration of the message signal at t interval. Okay, so if I if I write this, okay, if I write this, I will write this with our modulated signal FMT is equal to AC cos 25 FCT plus here you have 25 F delta, no, deviation. So we know that within this deviation, AM value is there. Okay. So AM value is already there. This is frequency deviation, and the AM value is already there. So we have to write the nominalized signal. That is, we have to divide this signal by AM. Okay. So we have sine 25 FMT divided by 25 FM. Okay, so this 25 cancel out. Okay, and we have XFMT is equal to AC cos 25 FCT plus F delta by Fm. Okay, so what is F delta by Fm? It is F delta by Fm. What is that? It is modulation index, MF. No. So here we have modulation index, MF. Sometimes it is called beta. Okay, I think we have used the beta. No? Beta sine 25 Fm. So this is the modulated signal. Okay, so this beta is modulation index and it is equal to 2.5. Yeah. So this is 2.5 and we know that this AC we know it is 40. This FC we know it is 10,000 and this FM we know it is 100 Hertz. No? So we can write the modulated signal. Okay. So I think that is okay. Okay. So already we have discussed this thing in our lecture part. So we are not going to discuss that. Okay. So we have to find the instantaneous frequency. I think that is also we have done in our lecture session. Okay. That is 4. No? So what is the instantaneous frequency? So for FM signal, instantaneous frequency is given by Fc plus F delta xt. No? Okay. So please remember that this F delta has AM, already has AM. So if I write the instantaneous frequency, I can write this as Fc plus F delta already have AM. Okay. So actually we are given here 2 point the modulation index. Okay. So we have to find the F delta. Okay. So we can find it. Okay. So F delta is equal to modulation index into modulating signal frequency. Okay. So it is equal to beta is equal to 2.5 and this FM is equal to 100. So this is the frequency deviation, that is 250. Okay, so this is the frequency deviation, F delta. So I put 250 here and instead of xt, okay, so this is our xt. This is our xt message signal. Here it is donate as here it is represent as empty. Okay. So it is 20 cos 2500 t. Okay. So I have to ignore this AM part because AM is already there. So only cos 2500 t should be right here. No? So it is cos 2500 t. Okay. So this is 10,000. No? Okay. So using this, you can find the instantaneous frequency. It is very easy. For example, if you want to find the instantaneous frequency at t is equal to 0.1 second, so you can directly find it 0.1. So it is 10,000 plus 250 cos 2500. This t is 0.1, no? 0.1. Okay. So all the terms you know. Okay. So you can simplify this using a calculator and find the relevant instantaneous frequency. Okay. So likewise, you can find all relevant instantaneous frequency. Okay. Okay. So again, we asked to find the power of the modulated signal for both cases. Okay. Actually, this is not 5 delta. It should be F delta, okay. F delta is maximum and 5/2, okay. So anyway, you know that for a frequency modulation signal and phase modulation signal, amplitude not changing. So amplitude is the signal amplitude is equal to carrier signal amplitude, okay. So always we have the transmit power as half AC square, okay. So it is not depend on this message signal or modulation index, okay. It is only depend on the carrier signal amplitude, AC square, okay. So you can easily find the power of the modulated signal, okay. Then this one, find the frequency spectrum of the signal, okay. So you can, I hope you can use two method. We know two method. Two, we have discussed two method to find the frequency spectrum, okay, of frequency modulated signal, okay. So this is for tone modulation, no? Only only one tone is used as a message signal, okay. In another word, we choose a sinusoidal signal for message signal. So that is tone modulation, one tone modulation, signal tone modulation, okay. So actually we have two two spectrum, okay. One is I think you can remember that we have not derived, okay, but we have derived it for phase modulation that signal, okay, phase modulated signal. But for FM we doesn't derive it because no need to derive the frequency frequency spectrum of FM signal for tone modulation or something, okay. So I think you can remember that the frequency modulated signal frequency, the spectrum we can get, remember, okay, using this, no, this is one method. Okay, so this is the spectrum for phase modulated signal and FM. In case of FM, this 5F, so here 5F minus FC, 5F is equal to minus J F delta XF by F. Okay, so here for FM, okay, 5F is equal to minus J F delta XF by F, okay. So we have to find these terms only, okay, because other terms already all are given, okay. So we have to find these terms only. So for that we have to find the XF. So what is this XF? Fourier transform of the message signal, Fourier transform of MT, okay. So it is cosine signal, okay. It is cosine signal, cos 25F0 T type signal, okay. So we know that we have derived this, okay. You can go through that lecture and find, okay. For signal and system also we have derived this cos 25F0 T, it is half delta F minus F0 plus half delta F plus F0. No? So you know that F0, what is the F0? So you can find the frequency, the Fourier transform of this cos signal, okay. And AM is there, so here AM should be here, okay. and you can find this one easily, xf. Okay, so here you have to substitute f minus fc. So you have to, so 5 f minus fc is equal to, so we have to simply shift this, no? So here delta f minus f naught, okay, minus f naught minus fc plus am by 2 am by 2 am, yeah, am by 2 delta f plus f naught minus fc. Okay, so I will write it here, plus half delta f plus f naught. So here we have f plus f naught minus fc. Okay, so you can find this. Okay, so you have to substitute it here. Okay, then you can find the frequency spectrum. Okay, so this is one method. Another method is using the Bessel function representation. Okay, so Bessel function representation also we have derived it. Okay, please go through that tutorial session. Okay, find in the Bessel function representation for frequency modulated signal. Okay, so you can find it. Okay, so we have derived. Okay, we have derived the frequency spectrum for frequency modulated signal. It is like this, n from minus infinity to plus infinity. AC, this AC is the amplitude of the carrier signal, Jn beta. So this is first kind Bessel function by 2, and you have delta f minus fc plus nfm. Okay, plus delta f plus fc plus nfm. Okay, so this kind of spectrum we have derived. Okay, we have derived. Actually, I think this is easy, much easy. Okay, so this is derived for the message signal AM cos 25 FMT type signal. Okay, so our signal is also in this type, AM cos 25 FMT. Okay, so we know the FM, we know FC, okay, and we know AC. We can find the Bessel function, okay, using the Bessel table. Then you can find the spectrum, no? Okay, so I think this method is easy. For example, this beta is modulation index. Okay, so this beta is modulation index. Already we know that. Okay, so if we draw the spectrum, okay, for few terms, okay, so I will draw from n equals 0 to 1, 2, 3 terms. Okay, so this is f. Okay, this is f. Okay, so for n is equal to 0, okay, that means here n should be minus infinity to plus infinity. Okay, but you don't need to write all the terms. We can't write all the terms. Okay, so if you write the few terms, it is okay. Okay, you can get the full marks. Okay, so I will write 2 or 3 terms. Okay, so it is like this. Okay, so I'm not going to put the value here, AC by 2, FM, FC. So we already know these terms. Okay, these are given. Okay, so I will write it in general form. Okay, so here for n is equal to 0, you can see that. Okay, you can see that this is AC. So n is equal to 0, J0, beta is equal to 2.5. So we have this kind of graph. Okay, this kind of value, AC J0 2.5 by 2. Okay, so you can find this value using the Bessel function table. Okay, so then you can find the term. Okay, AC and AC, you know, so you can find the term here. What is the value here? And here it is FC minus FC plus N is 0. So it is F minus FC. Okay, so here it is shifted to this way from 0 to FC. This way it is shifted. Okay, and for these terms, it is shifting this way. Okay, this way. That is plus FC. So here FC is here. Okay, so here you also will get the same like this. Okay, and if you find the value for n is equal to 1, okay, so what is the value here? So some value is there, so it is equal to AC by 2 J 1 2.5. Okay, and what is the value here? What is the value here? It is FC plus 1 FM. So it is FC minus FC plus FM. Okay, so it is shifted to here, no? FC plus FM. Okay, in same way, the minus side also there, FC plus FM, and this value will get for that part also. Okay, like this. Okay, so if I find the n is equal to 3 value, okay, so I will have AC by 2 J3 2.5. So you can find this value. You can find this value using the Bessel function, and we know this AC also. Okay, so you can find this value. Okay, and what is the value here? So n is equal to 3. So it is FC 3 FM. No, so here it is FC plus 3 FM value. So in the same way, in minus side also, because of this term, generate another impulse here also. It is FC plus 3 FM. This is minus. Okay, these are minus. Okay, and the value is same, this one, that is AC by 2 J3 2.5. Okay, so likewise you can draw the spectrum very easily. So I hope you get it. Okay, so you no need to do any derivation. You have to keep remember. Okay, so I hope in your examination these things will be given. Okay, this derivation will be given to evaluate the form. Otherwise, I think it is open book test. No? So you can have the notes. Okay, you no need to keep remember these things. Just you can write it and apply for the question. Okay. So I hope this is okay. This question is okay, and it is easy question. Okay, thank you.